For decades, really for centuries, physicists have been on this grand quest for one singular theory to rule them all. A theory of everything. But what if the answer isn't some crazy complex math equation, but something you can almost touch? What if the entire universe is, quite literally, a machine? I mean, really think about that. Is the universe a machine? Let's throw out the idea of these mysterious forces acting across empty space. Instead, let's imagine that everything—gravity, light, you, me— it's all just the result of pushing, pulling, and twisting a single universal substance. So, this theory we're diving into gives the substance a name: the void network. Now, don't let the word void fool you. It's not empty at all. In fact, it's the opposite. Think of it like the very fabric of reality, a super dense packing of these tiny, tiny grains. Our whole universe is just built from the stresses and strains happening inside this one material. Okay, so to see if this whole idea even holds water, we've got to look for clues. And we're going to start with a force we all know and love: electromagnetism. In a mechanical universe, where does something like that even come from? This is where it gets really cool. In this model, an electron isn't just a point with some magical property we call charge. No, it's a physical knot, a tiny whirlpool in the void network that creates a permanent physical twist in the fabric all around it. So the electric field? It's literally a field of twisty stress. Right, so if electricity is a static twist just sitting there, what's magnetism? Well, that's what happens when the twist starts moving or changing. It creates a flow, a little vortex in the void network. It's just a beautiful way to see how these two forces are really just two sides of the same mechanical coin. One is static, the other is dynamic. Look, that's a nice story, but here's where this whole thing gets some serious teeth. A good theory doesn't just describe what we already see, it has to make predictions we can actually go out and test. And this framework claims it can calculate one of the most important numbers in all of physics using nothing but the geometry of how these little grains are packed together. So just by looking at the geometry of the void network, how these grains stack up and how they transmit that twisty stress, the theory calculates that this fundamental constant, the inverse fine structure constant, should be about 138.1. Remember, that number comes from pure geometry, nothing else. And what's the number we've actually measured in labs for decades? 137.036. I mean, come on, that's an error of less than 1%. That is an incredibly close prediction for a number that, in our standard model of physics, we have no way of predicting. We can only measure it. This is a huge clue that we might actually be onto something here. Okay, let's keep going. Clue number 2. We're moving from electromagnetism to the heavyweight champion of forces, the strong force. You know, the cosmic superglue that holds the nucleus of every atom together.
So why is the strong force so different? Why doesn't it get weaker the farther you go, like gravity or electromagnetism? Well, the mechanical answer is all about how this stress gets transmitted. Electromagnetism is a twist, and that twist spreads out in every direction, so it gets weaker. But the strong force? That's a direct pull. It's tensile stress. And in a granular material like our void network, that tension forms these one-dimensional force chains.
And here's the kicker. If you try to pull two quarks apart, it's exactly like pulling on the ends of a chain. The tension is the same all the way down the line, no matter how long the chain gets. This is why you can never, ever pull a single quark out by itself. The force just doesn't let up. It's a shockingly simple, mechanical answer to a really deep quantum mystery. All right, time for our third and final clue. And honestly, this is the weirdest one of the bunch. The weak force. It's the one behind radioactive decay, and it has this one bizarre habit that has kept physicists scratching their heads for a long, long time. So the weak force can literally change one particle into another. In our mechanical model, where particles are just knots in the fabric of space, that means the knot is actually untying a bit of itself and reconfiguring its shape. And for that to happen, the little grains of the void network have to physically slip past each other. It's a kind of shear. And here it is, the big mystery. The weak force is incredibly picky. It only interacts with what we call left-handed particles. It completely ignores their right-handed mirror images. They could be right there and the weak force just doesn't see them. It's called parity violation. Why on earth would nature have such a strange bias? The answer this theory gives is just beautiful, and it's all about geometry. Think about trying to turn a screw. If the threads on the screw match the threads in the hole, it turns smoothly. That's our left-handed particle. Its knot structure lines up perfectly with the void network's geometry, which lets it slip and decay. But a right-handed particle? That's like trying to force a screw into the wrong way thread. It's cross-threaded. Its geometry fights the vacuum structure, so it gets locked out. It just can't slip. And that leads to this absolutely stunning conclusion. The weak force isn't biased at all. The vacuum is. The very fabric of reality, the space we live in, has a built-in, geometric left-handedness to it. Parity isn't being violated by a force. It's just a fundamental feature of the universe's architecture. So let's take a step back. We've followed the clues, we've seen how electromagnetism, the strong force, and the bizarre weak force could all just be simple mechanical actions. It's time to put it all together. And here it is. This is the master blueprint, the whole shebang. 5 phenomena that seem totally different, all explained as different kinds of stress on one single material. The strong force is a pull, like a chain. Electromagnetism is a twist. The weak force is a slip, and we can even take it further. The theory suggests gravity is just the material expanding, and inertia is just the feeling of drag as you move through this stuff. One material, 5 behaviors. It's the entire cosmic machine, right here in one simple table. And that leaves us with one final, absolutely mind-bending thought to chew on. If this is even remotely close to being right, if reality itself is a mechanical, programmable material, then the laws of nature aren't just rules we have to obey, they're just the properties of a substance. And maybe, just maybe, one day, they could be engineered. What could we build if we could control the fabric of space-time itself?